Hello friends, I welcome you in lecture number 7 on complex integration. In this lecture also we will discuss one more problem on contour integrals or complex line integrals. In this problem we are going to integrate this function f of z equal to square of absolute value of z along the contour C, which is a square in the xy plane. And we know that if z is x plus iy, then absolute value of z is given by square root of x square plus y square, and if we take square on both sides we have mod z square equal to x square plus y square, and we want to integrate this function along the square which is the square with vertices 0 0 1 0 1 1 and 0 1. So this contour C is nothing but boundary of the square with these vertices. So first we try to sketch this boundary of the square with these vertices, and then we will have the idea about the given contour. So I roughly sketch this square with all these vertices. Suppose this is imaginary axis or y axis, this is real axis or x axis, and we have to consider square with vertices 0 0, this is 0 0. Suppose this much distance is 1, then we have 0 1 here, and suppose this much distance is 1, then this point is 1 comma 0, and at this point we have x equal to 1 and y equal to 1. So we have this square with these vertices, and we have to integrate along this square along the boundary of this square. So our first vertex is 0 0, so we will consider in anti-clockwise direction. Starting with 0 0 we go in this direction, then 1 0, then 1 1 and 0 1, and we will integrate along this direction. So our contour C is nothing but this boundary of the square with these 4 vertices. So this is our contour C, having these 4 line segments which are the boundaries of the square with these vertices. Now because we have a square with these 4 line segments, and on each line segment we will have different equations. For example, suppose we denote this by C1, line segment between 0 0 and 1 0. This is denoted by say C2, this is by C3, and this is by C4. Now this line segment C1 is along x-axis, and we know that along x-axis y is 0. So we will have description or representation of C1 as y equal to 0, and we are going in this direction. So here y becomes constant, it is 0, and x is changing. So at this point x is 0, and we are going in the increasing direction of x, and we are going up to this for C1. So x lies between 0 and 1. So this is the representation for C1. Similarly for C2, we can see that this distance is constant, it is 1. If we take any point on this line segment, then its distance from origin is 1. So here x becomes constant and y is changing. Y is changing from y equal to 0 to y equal to 1 in this direction. So we represent C2 by x equal to 1, and y lies between 0 and 1. Similarly for C3, we have to consider this direction. So along C3 we can see y becomes constant. If we take any point in this part, its distance from x-axis is 1. So for C3 we have y equal to 1, and x is decreasing. So here we have x starting from 1 and going in this direction towards 0. So x is from 1 to 0 for C3. and C4 is along y-axis. So we know that for y-axis x is always 0, and because we are going in this direction, we will consider y from y equal to 1 to y equal to 0, because we are going in this direction. So we are integrating along the contour C, which is the boundary of this square, and this boundary is nothing but union of these four curves C1, C2, C3 and C4. So given contour C is the union of all these four different line segments or different contours, and therefore integral along C will be equal to sum of integrals along C1, C2, C3 and C4, and the value of function is same, it is mod z square along each line segment. So first we write down given function is given that f of z is mod z square, and if we consider z equal to x plus iy, let z equal to x plus iy, then f of z is mod z square, that is x square plus y square. Now along different parts of this boundary or along different curves C1, C2, C3 and C4, this function will be different. For example, along C1 we will put y equal to 0, so this will become function of x. Along C2 we will put x equal to 1 and it will become function of y. Same thing for C3 and C4. So that we have to take care that integral will be different along different contours C1, C2, C3, C4, and similarly f of z will also be different depending upon the equations of C1, C2 and C3. And here we will require dz also, so this is also different for different contours. So what we can do, we can go along contours one by one. First we find out integral of f of z along C1. So along C1 y is 0 and x lies between 0 and 1. So here y equal to 0 and x is changing. So if we put y equal to 0 in f of z, we have f of z equal to x square, x is in between 0 and 1, and our z is x plus iy, but y is 0, so z becomes x, therefore dz by dx is 1, and therefore dz equal to dx. So integral of f of z along C1, therefore we will find out integrals of given function along C1, C2, C3 and C4. So here x is from 0 to 1, f of z is x square, dz is dx, so this becomes x cube by 3, and x is from 0 to 1 and we obtain 1 by 3. So we will do calculations along each contour, because function will be different along each contour, we will have different dz by dx along each contour. Along C2 we have x is 1 and y lies between 0 and 1. So here I write x is 1, 0 less than or equal to y less than or equal to 1. Now our function is f of z equal to x square plus y square, and x is 1, so square of 1 is 1, and we have f of z in terms of y. F of z is function of y, y lies between 0 and 1. Z is x plus iy. If we take x equal to 1, we have z equal to 1 plus iy, therefore dz by dy is derivative of 1 is 0, I, and derivative of y is 1. So along C2 dz will be replaced by I times dy, and f of z will be replaced by 1 plus y square, and limits of y will be from 0 to 1. So now we find out integral of f of z along C2. which becomes limits of y are from 0 to 1. F of z is 1 plus y square, dz is I dy. Now I is independent of y, it is constant, and integral of 1 plus y square is y plus y cube by 3, and limits of y are from 0 to 1. And therefore after calculations, f of z along C2 is I times, for y equal to 1 we have 1 plus 1 by 3, for y equal to 0 this is 0, and this is 3 plus 1, that is 4 by 3, and we have I. So integral along C2 is 4 into I divided by 3. Similarly we find out integral along C3, and along C3 we check what is equation for C3. C3 is given by y equal to 1 and x is from 1 to 0. So here we put y equal to 1 and x is from 1 to x equal to 0, and f of z, here C3 is y equal to 1, and what was C2? C2 was x equal to 1. So here along C2 we have x equal to 1, x becomes constant, therefore we have function of y. Here we have y equal to 1, so y becomes constant and we will have function of x, that is x square plus 1, and we will consider x from 1 to 0. Similarly z is x plus iy, y is 1, so we have x plus I, and if we find out derivative of z with respect to x, we have derivative of x is 1 and plus 0, therefore we will replace dz by dx. F of z is x square plus 1, limits of x are from x equal to 1 to x equal to 0. So now we can calculate integral along C3. Here be careful, x is going from 1 to 0, so here we will put lower limit of x as 1, upper limit as 0. F of z becomes x square plus 1 and dz becomes dx. Then this is simple integral, x cube plus x cube by 3 plus x, limits of x are from 1 to 0. For upper limit x equal to 0 will give us 0, minus for x equal to 1 we have 1 by 3 plus 1, and this is minus 4 by 3. So we have obtained integral along C3 of f of z is minus 4 divided by 3, and finally we integrate along C4. So along C4 we have x equal to 0 because it is on y axis, so x is 0 and y is from y equal to 1 to y equal to 0. So for C4 we have x equal to 0 and y is from 1 to y equal to 0. Because x is 0, f of z becomes, f of z is x square plus y square, and we put x equal to 0, so f of z is y square, and z is x plus iy, and x is 0, therefore we have iy, and if we take derivative of z with respect to y we have I, and therefore we will replace dz by I times dy, and f of z is y square and y is from 1 to 0. Therefore integral of f of z along C4, this is equal to limits of y are from 1 to 0, f of z along C4 is y square, and dz is I times dy. I is constant, integral of y square is y cube by 3, and limits are from lower limit is 1 here, upper limit is 0, and if we take y equal to 0 we have 0, minus for y equal to 1 we have 1 by 3, and this is minus I divided by 3. So we have obtained that integral of f of z along C4 is minus I divided by 3. Now as we have obtained integral along each boundary, we can find out integral of f of z over the boundary of this square by taking addition of all these integrals. Integral of f of z along C1 plus integral of f of z along C2 plus integral of f of z along C3, and then integral of f of z along C4. And we have obtained all these values that we sum here. Along C1 we have 1 by 3, and along C2 we have 4I by 3. So first we put 1 by 3 and 4I by 3. Here I have 4I divided by 3, and along C3 I have minus 4 by 3. So let me put that here, minus 4 by 3, and along C4 I have minus I divided by 3. And now we can combine 1 by 3 and minus 4 by 3, and plus we can take I common from these two, and we have 4 by 3 minus 1 by 3, and 1 by 3 minus 4 by 3 is minus 3 by 3, that is minus 1, plus here I have 4 minus 1, that is 3 by 3, and it is I. So this is our answer, integral of f of z along contour C, which is the boundary of this square with given vertices, is minus 1 plus I. So this is very interesting problem. We have seen that our boundary has different parts, and these different parts are different line segments, and each line segment has different representation. Therefore we are integrating along each line segment, and then we are taking their sum. So they can ask this type of problems also, and this is very easy, but you have to be careful whenever you are writing all these things. You have to take care, and one more thing, you have to go in anti-clockwise direction. If you are going in clockwise direction, then your answer will be negative. Suppose our answer along anti-clockwise direction is alpha, integral of f of z along contour C in anti-clockwise direction is alpha, then integral of f of z in clockwise direction is minus alpha. So we are always going in anti-clockwise direction, so here also we have to be careful. And you can see here I have taken limits of x from 1 to 0. So that is very important part here, because we are going in this direction. We will integrate from x equal to 1 to x equal to 0. Same thing here. Here also we are going in anti-clockwise direction, and in this direction y is changing from y equal to 1 to y equal to 0. So here also we have integrated from y equal to 1 to 0 instead of y equal to 0 to 1. So this direction is important, and you have to decide the limits of variable of integration according to this anti-clockwise direction. And if you are choosing clockwise direction, you have to consider negative of that answer. So this is all about this session. We will continue with this type of problems in upcoming lectures. Thanks for watching.